say no to the kind invitation from very close friends, and congratulations on setting up the new chapter for Al Jazair. Al Jazair is a great Arabic country we always admire and love. Some of my best colleagues in my workplace, Kamal, Abdul Halim, are all from Al Jazair, and they are very extremely professional, hardworking, great people to work with. So I always admire supporting any initiative in the community, especially if it's from an Arab country. That makes us all proud of that progress. I think I will go through a lot of content, so I will try to be very fast, but please write on the chat any questions you have so we can get back to it. I understand that the audience is all cyber professionals, but with different backgrounds. Some of them are energy sector, some of them are IT, who are interested in OT, some of them are OT core professionals, and they want to see what's happening outside globally and in the region, so they update their knowledge. So I've tried to put together a nice content deck that should explain for the maximum, to include the maximum of the audience in terms of the expectations. So we will cover what is OT cyber, why it's difficult to protect OT, and the threats and challenges we are all facing in the region and in the Middle East specifically. We will cover the standards out there in the market and what is the model architecture or the Purdue model for OT security architecture. We will also be covering security versus safety, and which is a very big question and a very big topic in the domain of energy sector and any critical national infrastructure, how security can impact safety. And in the last module, we'll be covering OT security monitoring, or the SOC, the OT SOC, and how to build one, and how this SOC is different from a typical IT SOC, or how it can work with an IT SOC, because there are some differences. So without wasting the audience time, I know it's late and everyone wants to go back to his family. I'll try to go straight to the point. First, some definitions. There are many terms in the industry right now. Some of us use OT or operational technology. Some people use ICS, which is industrial control systems. So I want to start with this slide, which explains the relationship. In the current modern time and age, the biggest term is IoT, Internet of Things. Everything else falls under IoT. And in the future, I predict that there will be no layers and no boundaries that you are seeing on the screen. It will be all a digital ecosystem of any company. There will be no more IT versus OT. I have the corporate, I have the plant, and they're not talking to each other. Hello, I'm still audible? Just checking. Hello?
Yes, we can hear you. We can hear you.
Good.
Yes, we can hear you.
I heard someone drop. So I think overall, those boundaries will diminish. You will have a digital company, and you will need to secure it and protect it end to end. But for now, we have those boundaries. So we have OT, which is a subset of IoT. Those usually are the mission critical systems. باللغة العربية أنظمة التحكم الهامة أو الحرجة. Those are the control systems that oversee sensitive, procedures or processes like water, electricity, power grid, smart metering in the whole country. All those big topics are OT. Then we have ICS, industrial control systems, which is the industrial part of OT. For example, you might have a smart building system, smart building management system, how to manage a smart building with the elevators, with the air condition, with the electricity to the building, the fire and gas systems. Those are not ICS. This is OT, because OT is a big term. But for engineering purposes, like oil and gas company, liquefied natural gas company, electricity company, now we are getting closer to ICS, industrial control system, and that's the term industrial. Then we have SCADA systems, supervisory control and data acquisition systems, which are common in a plant to manage the plant. And if you have multiple locations to manage and multiple SCADA systems, then you will have DCS, distributed control system. And usually you see this in electricity domain, in the electricity industry, where they have the north region network, the south region network, and each region is very complicated, lots of substations, power transmission, power generation. To connect all of those things together, you will have a DCS. You can have it also in a plant if you have a very large petroleum complex and you have multiple locations in the complex. One is producing ethylene, one is using polyethylene, one is refining. So in that case, if you want to connect multiple dots together, you might have a DCS. The component that is used to, if you go a little bit lower in the levels, and I have more slides to explain that, you will have PLCs, which are programmable logical controllers. Those are very small computers executing a specific task. For example, opening a valve or closing a valve, or running a motor, or running a reservoir, opening the pressure, or increasing the pressure, or reducing the pressure. This is the function of a PLC. So multiple PLCs can make a SCADA system, and a big SCADA system with all communication can make an ICS. If an ICS is in the engineering industry, that's ICS. If it has multiple sensors connect to it and a bigger ecosystem around it, this can be OT, and so on. There's one unique term, which is AMI, which is a smart metering or advanced metering infrastructure. This is only found in electricity grids where you have smart meters, العدادات الذكية. So you can have each home connected to a smart meter, and this meter is talking back to the energy company in a bi-directional way, so the load and the demand can be managed automatically over time. This is only unique to the electricity industry. So all of those systems are not new. They are in the world since the 60s, but recently they are under attack. We are seeing lots of attacks, and if we look, and I always use this example, if you look at Shamoon, Tuku, Flame, Stuxnet, probably Black Energy, many attacks that are only focused on OT have one thing in common. All of them happen in the Middle East. The main victims were in the Middle East. There are some exceptions, but the majority of this has been the Middle East. This can be because we are a region that depends on energy as the main source of income for the country. This can be because we are the weakest in security, and attackers always attack the weakest link. This can be because our countries do not have offensive capabilities, so they cannot retaliate or respond to the attack. So the attacker finds it comfortable, an easy target. I'm not afraid of any retaliation. Let me attack it again. Though all of those reasons might be the case, but for us as defenders, as the good guys, as the cyber people, we need to appreciate this position. We are under attack in a very sensitive region, so we need to be at the best level we can. Okay, another importance important topic we need to cover in OT as well. It's unlike IT. OT is very, the impact of an attack on OT system is not limited to the company which is the victim of this attack. You might have the impact of that cascading into the whole country. I will give you an example. If we have an attack on the energy production of a country in the Arab world, because of the importance of energy, you will find there might be no water in those countries because they use the energy to desalinate the seawater, especially in the Gulf region. So the water supply might be impacted. If I have no energy, I will have problems in transportation if I'm running metro and other services that use electricity. If I lose energy and electricity because I do not have any other supply, I don't have nuclear, I don't have other things, I might lose the entire telco infrastructure, which all runs on electricity. So an attack on energy might have a very bad impact on all sectors if this attack duration got long. Not just that, usually in some regions, the electricity network is even connected for the whole region. For example, in the Gulf, all the Gulf countries are on the same electricity grid. So if one country is under attack on the electricity grid and it fails, this will put a lot of pressure and load on all the other countries. This increases the value of OT, and this will never happen in IT, because if you are attacking a bank, for example, the bank is a victim. The whole country will not suffer. Maybe commercially they will suffer, but technology-wise, the impact will be limited compared to this. So how OT works? OT, as I said, is not new, or the systems running such services. They are here from the 60s, which is the first picture on the left side. But the communication at that time was purely electric, like electrical engineer, up and down, 0, 1, there's current or no current, that's it. Then in the 70s and 80s, we started to have what we call distributed age, where the likes of Siemens and Schneider and Honeywell started to bring some network protocols to connect the systems. But those protocols were proprietary protocols, meaning a Schneider system will speak a Schneider language. The protocol is Schneider. If it's a Honeywell system, it will speak Honeywell language. There was no TCP/IP yet. Now, in the late 80s and 90s and early 200s or 2000s, we are now in what we call networked age. And as you can see from this picture, it's not just because it's colored, but there are PCs, there's Wi-Fi, there is Windows, there is SQL, there's printers, modems, scanners, mobile applications. It's a completely different control room, doing the same function, but using a lot of computers. And that changed the whole thing. It made things easy, but also brought a lot of attacks and a lot of threats and risks, because we know IT is not 100% secure. So if you put IT in the field, it brings the challenges as well. Of course, it brings benefits, but also challenges. So how it actually works, and what do I see from this view? So if you go to a control room in any oil and gas company or electricity company, you will see this view. This view can be put on a big screen, and we call it HMI, Human Machine Interface. It's a simulation of the plant or the asset you are managing in a very graphical interface. You see the pumps. I will try to use the pointer here. So you will see the tanks, the reservoir. You see the pumps. You see the the filters. You will see the compressors. All of the items in the plant, you see them graphically. And the system is built to operate automatically within certain limits. So if there's a pressure between what we call set points, minimum and maximum, if it's within this range, the system can manage and can adapt and can change the equations and the input and output automatically. No need for a human intervention. But once there is an alarm and a set point is reaching maximum or it crosses the boundary, the operator need to intervene, the human engineer, like you see on the screen on the right, and he need to make some decisions within his knowledge and within his limit. Open a valve, close a valve, add more pressure, reduce the temperature. He will interact with the system to keep things stable and under control. This happens 24/7. A plant never stops. Production never stops. And I want you to remember those things, because this will lead into security challenges. So this is running 24/7, and this is how majority of the critical services are being provided. But what is behind the screen? How the engineer sees this data, where this data is coming from, and how it got there. So we can simplify this by this view. If you have this, or if you look at the right side, start from the bottom. You will have physical assets in the plant. This can be a machine, a valve, a motor, a compressor, anything, a pipeline. This can be a physical asset. Connected to the physical asset are some sensors, and we call them RTUs, remote terminal units. Those sensors have very simple function, which is measure specific inputs. For example, if this is a pipeline, what's the pressure? What's the temperature? What's the flow direction, right, left? What's the status of the valve, open, close? They are gathering intelligence. They send those RTUs send the intelligence to the PLC, which is the small computer in charge of this asset, or in this system, and it makes some decisions based on the pre-programmed that instructions that the engineer already gave it. So it's when you get a PLC, it's of course blank. Then the engineer puts some logic and configure it in a way to make some decisions. The PLCs, and you have thousands in the plant, 1,000 PLCs, 1,000 small computers. They share all of those decisions and the traffic and the pattern, everything they see from the RTU and the decisions they made. They share this back to the servers, or the ICS servers, or the OT servers. The servers aggregate all of this data from all the different sources and give it to you graphically on the HMI, which is a human machine interface, which is a Windows machine or a Unix machine. On top of it, you will have this diagram. All of the events and the decisions and the timestamps and the logs, everything that happened is recorded in a master database, which we call the historian. It's like the logbook or the record keeper of everything that happened in this process, from the moment it went live to the moment it is decommissioned and closed. So the entire life cycle of this asset is recorded here in this historian. So it has a lot of valuable information. Now, if you look at an RTU, which is the yellow one, which is the sensor, this is an image of an actual RTU. I hope you can see that it's a Linux machine. It's a Linux embedded system with RJ45. And you can start now thinking of the problem. So I have an OS like Linux, very, very deep in the plant, connected to RJ45 or Ethernet port, and carrying all of this traffic over TCP, all the way down to the plant. And those can be underground, by the way. Like in the pipeline, it's under the surface. It can be an offshore. It can be in the middle of the ocean. It can be anywhere. How to get there? That's a challenge. Okay, so let's go deeper. And now this RTU uses TCP/IP. It communicates using a famous protocol called Modbus. Anyone can download the manual of this asset or this PLC or this RTU. And this is a real case. I downloaded the manual. I read the manual. You can see here that you need to give it an IP. You need a subnet mask. You need a gateway. You need to configure the DNS. And you can admin this or manage it using username and password. What are the username and passwords? It's admin. I think you need to start thinking of the problem now. So I have a Linux asset, hundreds and thousands of them. I have them using TCP/IP, Modbus over TCP, and I will explain the problem with the protocol. But the access to that is admin, so it's not very secure password. I need to configure it with a typical IP setup, like configuring a computer. The question now, can I change this? Can I change this password? You'll be surprised that in many cases you cannot change the password. This is the vendor instruction not to change the password. In many cases, it's hard-coded. And as a security professional, you need to think of those problems now. So I have n number, thousands of assets, which I cannot change the password. And I can, maybe it's very hard for me to patch it because there are thousands of them and I have very small communication window with them and they're always in production. The plant is 24/7 running. How can I patch it and secure it if the plant is running? So let's get closer to see another problem, which is the protocol. But before that, the passwords in OT are a big problem. This is a sheet. Our pen testing teams have been gathering this. Over the years, we encounter many assets, ABB, Emerson, Hirschman, Moxa, Rockwell, Schneider, and I have a big list. And the devices, the model there, and you find everything is default password. You can see here, admin, private, root. It's very standard, very specific, published in the public sources, in the manual of those assets. You cannot change the password. In one very famous case, which is Stuxnet, one of the famous attacks, and I will explain it, They targeted Siemens system, S7, which is a product from Siemens. When they talked to Siemens, they said, do not change the password. If you want to change the password, you need to pay extra. You need to pay more. And imagine this is not a good response to get, because security should not be a commercial advantage, but it is, because changing a password in a PLC like that, you need to re-engineer a plant or a factory of maybe $2-3 billion to change the password and change the configuration across all of that. It's a big investment. So changing something very small like the password is not easy, especially in the old systems. In the new ones, they learned, and it's now much easier to change the password, but this is only in the assets that are built in the last maybe 5 to 8 years, but 15 years or 20 years old assets, it's not possible. Okay, so let's go to the protocol. There are many protocols that are used in the plant to communicate between the PLCs, the RTU, and the servers. But some of the famous ones are Modbus, which is TCP 502, that's the port, and Profinet, which is TCP 102. One of the challenges in OT is that the protocols have chronic problems. Number one, they are plain text. Most OT protocols are plain text, meaning they are not encrypted, meaning that anyone who are or is connected to the network can see the traffic, can sniff the traffic. Why it's not encrypted? Because if they added encryption, this will cause delay in the plant. The plant uses real-time data. I need milliseconds to know if there's a fire hazard or not. If I added encryption and it will slow down the communication, the alarm might trigger and I will lose control of the plant. It's very sensitive. So adding encryption is not easy in the plant. And if I have to add it, I must buy very powerful PLCs who have a very good computing power to encrypt on the fly and decrypt on the fly very fast, which will increase the cost of the whole plant. Again, if it's multi-billion, it will be more. So protocol, and also because no one thought of security in the old times, security was not in the engineering of the protocol, in the design. So there's no encryption. Second problem, they are authentication-less, meaning anyone in the network can send a message, broadcast a message to all the PLCs saying, I am the server, please take my command or take my instructions. There's no authentication between the nodes, so the PLC will not challenge me, telling me, prove to me that you are the server or show me the credentials that you are the server. No, it's configured that the master can say, I am the master. There's no challenge in that. Which is an advantage to the attacker, because the attacker can now sniff. It's not encrypted. He can change the commands because no one will challenge him, telling him why you are changing it. Everyone will follow the new command without hesitation. So again, those are design problems in the protocol. Okay, now we have seen the problems in the Windows machines and the databases and the open standards that are coming. We have seen the problems in the PLCs and the Unix machine, embedded Linux, sorry, and the problems in the protocol themselves. So I have problems in every layer. How hard is it to write a malware for such an environment? The bad news is that it's very easy to write a malware for OT, specific for OT. And if you don't have the skills, there are companies now like Gleg and others who sell you the OT malware for a price. And maybe a few years back, I contacted some of them to actually see if I can buy a malware. And they sent me a quotation of the malware with warranty and money back guarantee if the malware didn't work. So it's a business. They are saying it's for research purposes, but everyone knows there's a legitimate business behind it. I mean, bad business, of course. And again, I think companies like Gleg and Revun, they even have special OT attacks for the medical equipment in hospitals. The very advanced medical equipment that do autopsy and scanning and any advanced stuff. They have malware for that to give the doctor wrong readings, so he can give the wrong advice to the patient. And it's called MedPAC. And I think you can now start seeing why OT is more serious than IT, because OT can cause or lose lives. It can cause safety impact. If the plant goes on fire, or an oil and gas facility, we lose control over a plant, people can lose life, or we can lose people's life. If an attack like that happens in a hospital, we can have a very bad humanitarian problem for the patients. In a bank, or in a ministry, or a government entity, or a normal IT environment, you will lose confidential data, yes. You will lose money, yes. You will lose reputation, yes. But you will not lose lives. There's no attack in a bank that can kill people working in the bank. But yes, and you will see some attacks in the energy sector designed to kill people. And that's the high risk of OT. Okay, so I'll show you now a quick video on an experiment done many years ago, but it shows you how the idea was to physically damage a motor, a large motor, power generator, using a malware. So I will try to run the video now. So that video, I will explain it to you. And it was done in 2007, an experiment by Idaho National Labs. You will see on the right, that's a $2 million engine. And the malware is configured to overspin the rotor inside. You'll see the engine braking and some pieces flying, and it's shaking off the ground because it couldn't handle the pressure of the frequency of the motor, which is exceeding the limit. This was done through a USB. The scientists who did this experiment didn't know what to expect, so they were monitoring this from a very far location, and they had this white smoke as a signal of total damage to the equipment. So I think that experiment was built to show that a USB stick of $5 can damage an asset of $2 million. And it's very hard to find who did it, because forensics in OT is very, very hard. And the trick was very simple. The maximum rotation speed of that engine, let's say, was 6,000 RPM, 7,000 RPM, round per minute, or rotation per minute. Let's make it 15 RPMs. So it will explode, it will burn. And that was the basic idea behind the experiment. Okay, now we have seen the problems. Are they really happening outside, the scientist labs? Are they really happening in our current world? So let me show you some things. I think the IT/OT is converging since 2014. We are seeing a lot of systems coming together. Like I explained, the IT is now expanding, the technology is expanding, and that's bringing a lot of threats to the plant. Usually, if you go to a plant or company, an oil and gas company, the number of OT assets is usually 10 times the size of IT. If you have an oil and gas company, and in the IT, in the corporate, you have, let's say, 1,000 IPs, 1,000 machines and servers and everything. In the plant, it's easy to expect 10,000 connected assets, 10 times what you have in IT. In IT, we are very aware of products like Microsoft, Oracle, HP, SAP, and all of that. In the OT, you have Yokogawa, Siemens, ABB, Schneider, Rockwell Automation. All of them are components that are now connected to the TCP/IP inside the company. And the budget you need to operate, not just secure, just operate, is much, much more than the budget to operate IT. And that brings you the size, the size and the impact of OT. It's really massive in oil and gas companies, for example. Okay, so why security now is becoming a buzzword for OT? And we'll go through some of the incidents, but why it's now serious? It's serious because there's many factors happening. First, there's a push towards more intelligent operations. The companies now want IT and OT to talk to each other, so the management can see real-time data from the plant. They do not accept segregation like in the past, that IT and OT are separate now. They want this to be connected. I'm seeing a lot of, or the plants are seeing a lot of mobility, meaning people can walk around the plant with mobile devices, handheld, to get the scans remotely on their handhelds, or through drones, or a vendor to remotely access the plant for maintenance. No need to fly, especially in COVID times. This was a massive thing. Schneider or Honeywell people do not need to fly from Europe. They can access remotely to fix and make the upgrades. So how secure those connections? I now have standards, or we have standards in the industry on OT security. I have malwares and attacks happening in OT. So all of those new things are making cyber in OT a massive topic and a big topic. Okay, just to, before I show another video, maybe about the future threats and then the actual threats we're seeing a lot of identity access management in OT. Who have access to what? Blockchain, unidirectional gateways, or specific firewalls in OT that allow traffic in one way only. We're seeing cloud being coming very powerfully or very fast to OT. I'm seeing also machine learning and artificial intelligence. All of this is pushing the OT teams to open up and embrace new technologies. And this again increases the threats, but the whole industry is pushing towards all of those topics on the screen. Everyone wants to use cloud. Everyone wants to use artificial intelligence. Everyone wants to use, identity, digital smart identity. That means security topic in the field, in the plant, will only increase and increase. So let me show you another video to also give you another challenge. Once we adapt more IT and more real-time communication, what can go wrong and how fast things can go wrong? This experiment was done by a US company. It's called IOActive, and they simulated smart meters. So they took, it's an actual experiment. There is a smart city in the US called Boulder in the state of Colorado. They have 20,000 homes connected to smart meters, so 20,000 smart meters. The smart meters are configured to communicate with each other, and each meter will take the readings of the neighbors and relay the message to the next meter, the next meter, and the next meter, all the way to the actual control tower of the electricity company. So each meter will take the reading of the, let's say, the neighbor on the right and pass it to the left. This is how it's built. And they will take the reader of the meter and then forward it, cascade it one by one, all the way back to the actual electricity company. So they can expect the demand. Maybe at night, people want more electricity, so they need to increase production. But they also have one feature, which we call it remote shutdown. If one customer is not paying his bills, the monthly subscription for the electricity, and he missed it a few times, they have the ability in the meter to shut down electricity on that customer alone, remotely. No need to send an engineer to cut down the electricity. They can do it from the control center. So that experiment on the screen is simulating something. It's simulating what if a malware spreads using this communication protocol throughout all the meters. So the green dots are the healthy smart meters connected to 20,000 homes. The red dots are infected smart meters. And you can see now how many seconds it will take to infect 20,000 homes. And the malware was configured to shut down the electricity on that home. It can be a hospital, it can be school, it can be home, it can be any place connected to the smart meter. If you look at the counter, you will see it almost took around 30, 40 seconds only. So less than 1 minute to shut down electricity on an entire city. Now, from a cyber perspective, what time as a SOC analyst do you have to interact? It's very, very hard to detect an attack and make a decision in 30 seconds before the malware spreads. So you have to think in a different way to stop this from happening. And I will try to explain how you can do that. But from a business perspective, why the malware was successful? The malware here in this model was successful because all the smart meters were identical, the same vendor, the same configuration, same firmware. Why the company did it like that? To manage it in an easy way. I need to train my support staff to support this meter. I cannot train them on 5, 6 products. I want to train them on 1 meter, one configuration. It makes sense from a business wise, but it's not a good idea from a security wise, because now one attack can hit everything because they are all using the same infrastructure and the same setup. Okay, now let's go to the actual attacks that happened. As you can see from this timeline, and it's not everything, those are just the published attacks. We have seen OT attacks since 2008. The most famous one was 2010, which is the very, very famous Stuxnet. Stuxnet was an attack designed to stop the nuclear reactors in Iran, attacking the Siemens PLCs, the small computer we explained in the beginning, asking the PLC to rotate a certain centrifuge or تخصيب الuranium, a device to improve the purity of uranium, to increase the rotation above the limit to damage that engine or damage that motor. So by doing this, they stopped the program for a few years. That was all public news later, but it was very famous because it was the first successful on-purpose attack against an OT system. A few years later, 2012, we had 2 attacks, one on Aramco, one on RasGas. The intention was to have access to some sensitive data in the oil and gas industry, and the malware was configured to wipe out and delete every OT configuration once the objective is successful. Everything was wiped, all the machines, all the servers, all the HMIs, everything. The switches, the routers, the firewalls, everything was cleaned, wiped, no configuration. The configuration file gone. So they had to rebuild everything. In Aramco's case, and all this public information, they lost around 30,000 computers. And they had to rebuild it from scratch. And you can imagine the cost. And the worst attack for me, and the one that really is a wake-up alarm, is this one, which is the Sadara chemical attack. This is an attack, and I have a slide on it, that was targeting the safety systems, the safety shutdown system of a petrochemical company called Sadara Chemical. When you target a safety system in a plant, you are not going after money. You do not need money, or you're not stealing money. You're not stealing information. You are stopping or damaging the airbag system in a car. This is the equivalent of shutting down the seat. A car will have seat belt and airbag to protect the passenger or the driver. Oil and gas plants and electricity sector and all the engineering sector, they have something called safety shutdown. It's a system designed to safely shut down the plant if there is a threat. So there's no explosion and no fire. It's like the safety belt or the airbag. So if we have a malware designed to kill the safety system, this is a malware designed to hurt and not after any money or any gain, except hurting. And that makes it very, very serious. And that attack is real, and it happened, and it's recorded and published. A few years later, we have a series of attacks against the Ukrainian power grid to shut down the entire electricity network of Ukraine. This started in 2015. It happened 3 times, at least, for the same company. So the same company was hit 3 times. I have a video that will show how it was behaving, but it teaches you something, that maybe the initial attack in 2015 by a specific country was to test how this network is built. And the attack was only for that purpose. The second attack was to test what can I do or what I cannot do. And then the third attack, just before the war, is to cripple down and cut the entire electricity because of the experience I gained from the previous 2 attempts. So I think OT attacks are also very unique in a way. You will find attacks that are staged attacks. You know, it's like I am learning about you, so at one point I can hurt you where it damages the most. And I have some examples on that as well. So on Stuxnet, there's a book published, and it's very famous scientist, Ralph Wagner, and he's a German, and he was analyzing the attack, and he called it "How to Kill a Centrifuge," a technical analysis of this. If you read this, you will find that every single picture that was published about the program in media, in news, the presidential visit, anything and everything was analyzed. When Iranian TV was showcasing the plant and celebrating the opening of the asset and the factory, the attackers, frame by frame, analyzed everything that showed in the background. The products, the models, the vendors, the design, the set points you can see here, everything was analyzed and used to make an attack that will work only for them. So the Stuxnet attack, which is a virus, it's published online. It was leaked online now. If you run it in any plant, in anywhere in the world, it will do nothing. But if you run it in this particular network, it will kill this network. It's like a lab-engineered flu virus, and you spray it in the room only to infect one person in the room. Everyone else in the room will not be infected. Or, sorry, will be infected, but it will show no symptoms, it will do nothing. But on that person, it will really damage his lung, for example. So that is how detailed those attacks are really configured and built. Okay, so let's go to the Ukrainian power grid. And before I show you the video and explain how that attack happened, if you analyze all the OT attacks, you will find that there is a reason behind those attacks, and very rare it's a financially driven reason. Unlike criminal groups who steal credit cards or threaten you for your personal pictures, or they want to publish your secrets, so they ask you for ransomware. This doesn't happen in OT. In OT, you can find attacks that have a purpose. A purpose can be, very sensitive, like damaging the equipment, like the example of the video we have seen. That's a purpose. That's an objective. Another objective, it can be a competitive race between 2 companies or 2 countries to damage the product quality that you're making, so you lose the market. One example, there's a very famous pharmaceutical product, يعني عقار طبي اسمه paracetamol. Paracetamol, if the purity of your product is 98%, the price is 78 euros. If the purity is 100%, it's 650,000 euros. So an attacker can attack your plant for pharmaceutical, يعني شركة دواء, to lower the quality of the product. If 1%, this company is out of business completely. Another type of attacks is to attack for the purpose of causing public safety problems. I can play, or the attack, not me. I do not have the skill.
Excuse me, Omar.
Yes.
Omar, it remains only 5 minutes, because we will
Sure.
take the
I will
5
go
last
faster.
minutes to take questions. Thank you.
Sure, I will run faster. So you can have a safety-oriented attack to damage the safety of the plant and people around it. Let me go faster then. Maybe I will skip that video. Okay, that attack in Ukraine it started by a phishing attack to the IT people requesting access to a certain jump server, and they were giving that access because they took the identity of someone else, and using that they log in, they have a successful login through VPN, they stole the credentials, and then they moved inside the company over 6 months. So that end-to-end cycle was 6 months long. I will try to skip this. This is a safety attack that happened in Sadara Chemical. You can see this is again published. The source here is CyberArk. All the details about the attacks are not confidential anymore. You can see that there was a problem in the design of the plant. There was one engineering, one remote desktop station that had 2 network cards, one connected to this network and the other one connected straight to the safety network, bypassing all the firewalls. So it was an engineering mistake or a design mistake. Once the attacker had access to that station, they can bypass everything because it has a network card with a segment access or IP segment to the engineering station of the safety system. Let me move faster. Yeah, now maybe let's go to the standards. There are many standards in the world right now to help you secure your company, design it in the proper way, protect it in the proper way. The famous ones are NIST 800, 82, and that's the number 800, all public, you can download it. The also very famous one is the ISO 99, and the new name is IEC 62443. Those are the most popular standards. Then, and they are multi-industry. They can work in water, electricity, petroleum, petrochemical, everything. For electricity sector only, you have the NERC SIP. That's a standard only for electricity industry. This one is for the natural gas and the pipeline, and this one is for the normal IT security, but it can help as well. I'll try to move faster. We are seeing a trend in many countries developing their own OT standards. Why developing their own? Because each country has its own limitations. Maybe I do not have budget. Maybe I do not have enough people. Maybe I do not have solutions that I can trust. So I need to develop a standard that is fit for my national needs. And many countries, especially in the Gulf, because they depend on oil, develop their own national standards. If you compare the standards, some of them are very identical in some areas, some of them are not identical. For example, across all standards, if you compare them around, for example, encryption, some of them are mandating encryption, some of them are not mandating encryption because of the reasons I explained. I will skip to the Purdue model. Okay, so now this is how one of the famous standards, which is ISO 99, tells us to design the plant. The plant should not be, or my OT network should not be a flat network. It should be segregated into layers and sections. Starting from the bottom, you have level 0. Those are the physical equipment. Those are the instrumentation, pumps, valves, everything. Then you have level 1, which is the PLCs. All the PLCs should be in this layer. Then you have switches and firewalls. Then you have level 2, which is the HMI, or the human-machine interface, the one with the graphical interface to manage the PLCs. Then you should have firewalls to create a layer called the DMZ layer, or level 3. Level 3 is where you put your SOC, your SIM, of course, antivirus, IDS, historian, any control and security appliance for the whole company or the whole plant can be placed in level 3. And then another firewall before you reach IT. So your DMZ is like in a sandwich between 2 firewalls. This is how you secure it. And now vertically also, you split your plant into what you call it zones. In the language of ISO 99, they call it zones. So we have zone 1, zone 2, zone 3. Why not put the whole plant as one zone? So if you have an attack and it's hitting this asset, you seclude and you protect and you maybe lose only this zone and you do not lose everything. So by zoning your IP structure, you limit the damage of the impact into a particular zone and you do not lose everything. When you apply this to your own company, you will find weaknesses. You will find, okay, now I have a zone here that is it's too much, or it's crossing the line of 2 and 3. I need to stop it, and those are the things you need to fix. For example, that's a company here before ISO 99 application or applying the methodology, and after. You can see now it's much better segregated, very separated into levels. To move from, this was a flat network, this is now 3.5 layers, which is up to the DMZ. Or this transition takes 4 years because it's a live plant, it's running. So to transition it, it's a step-by-step process, and it's not an easy process, but companies are doing it. I will skip now, but I will try to move faster into the SOC probably. Okay, SOC. In OT space, you need some components to activate your SOC. Let me go straight to the components. Yeah, here. So to have a proper SOC, you need SIM, of course, and you need to have some sensors. To have the sensors, you're usually placing them, which are those orange boxes, at level 1, level 2. You need to put the sensors there. And everything from those sensors is collected at level 3. And all of this feeds the SIM. So the SIM will take the feed from those sensors. The sensor will tell him what traffic is happening, what is normal, what is abnormal. Someone is scanning, someone is downloading, someone is changing the configuration, someone is putting a wrong command in the wrong time of the day. They learn what is normal, and then they tell you what is not normal. So the SIM to work will need those sensors. They will need the firewall logs, switches, DNS, historian feeds, many things to come together to give the SOC the right visibility. When you design your SOC, you have options. You can have an active agent, or active agentless, or passive. I will start with the passive. Passive is a sensor that just listens to the network, does not interact with anything, just listening. So that's why it's called passive. Then you have active with agent. It's an agent that is not just listening, but also asking questions. They are asking the asset, what's happening? Can you tell me? Can you please give me this? Who is the last member operator who joined or logged on? What was the last firmware signature you downloaded? It is interacting with the asset with an agent installed on the HMIs or on the server. You can have an active setup, but without an agent. So nothing is installed on the Windows machines or the servers, but maybe only from the network. It is talking to them through the network, but it's not connected to the OS. It's nothing installed on the OS itself. That's why we call it agentless. Each one has its own pros and cons. Most people like passive. Why? Because it's the safest approach. No one wants to touch a plant that is running. I do not know how it will react if I put an agent or whatever. Let me put a passive, just listening to what's happening, and it's a safe approach. I will try to jump
Excuse me,
into
Omar.
yes.
Yeah, you know, we are out of time. Exactly.
Okay,
Let's
sorry.
I suggest to take 1 or 2 questions, and
Sure.
after that we can close the meeting. Excellent.
No
The
worries.
first one is there is the question from Adel bin Muhammad. He is asking for talking about treat an attack that manages to compromise emergency shutdown system. What is the best advice to safeguard SES systems from such attacks?
Very good question. So I think the best advice is to isolate your safety systems, the SIS network. I have seen some companies putting diodes to allow only traffic one way, which is out. There's nothing coming in. So it's a one-way firewall, which we call it data diode. In another case, they really give this a separate IP structure, completely separate from the plant, and they protect it as their crown jewel with the maximum security, maximum firewalls, maximum rules, 24/7 monitoring to really protect your SIS system. It should not be on the same network like your other production systems. It should be always separated and isolated.
Excellent. We will take a second one, and it will be the last one, unfortunately.
Sure.
What security level is recommended for oil and gas industries? I think the security level, we are talking about those which are listed in the ISO 62443.
You mean if the question is what are the security levels in the company, in the architecture? I think we've mentioned that in the design. So those are the levels. If level 1 to 3.5. If the question is what is a good level of security I should accept, then it's based on your risk assessment. You need to do a risk assessment, and based on the risk, you can say I am under attack. I have a bad network, so my risk is high. So I need to go higher. You might say I'm not under attack, and I have a very good acceptable level of assets and protections and controls. I have a SIM, I have a firewalls, I have antiviruses. Then my risk level is moderate and it's acceptable. So each company has its own risk rating according to many factors. So I cannot say what is a good level to stop. You should always try to improve and improve and improve.
Excellent. Thank you, Omar. Over to you, Sofiane, for closing.
Yes, thank you. Thank you, Omar. Thank you, Omar, for this fantastic talk. We hope that all have
sorry,
enjoyed.
I apologize I couldn't finish. I took more time than required.
No problem. And we hope that all have enjoyed this webinar session. For our next chapter webinar, we will have an exciting session on cloud security and cloud audit training and certification. If you have any question, feel free to contact us by email. We will get back to you for all questions posted on the chat. And again, thank you and see you soon, inshallah. Thank you very much.
Thank you, everyone. Take care.
Thank you, everyone. Bye.
Thank you. Bye.
Thank you very much.
Thank you.
Thank you. Thank you.
Thank you all. Goodbye.
Thank you.
Thank you.
Thank you and goodbye.